The universe expands, yet the truth remains, still within.
What if reality is not what we think? What if reality is not what it seems? Every day we wake up, look around, and assume that the world we see is exactly what exists. We see solid objects, empty space between them, and time flowing forward from the past toward the future. Our senses give us the impression that the universe is stable, predictable, and made of tangible things that behave according to simple rules. For most of human history, this seemed obvious. The world looked solid, and so it was assumed to be solid. Space appeared empty, and so it was believed to be empty. Time seemed constant, and so it was treated as something universal and absolute. But as science progressed and physicists began investigating the deeper structure of reality, a surprising picture emerged. The universe turned out to be far stranger than our everyday experiences suggest. One of the first shocks came when scientists began studying atoms. At the beginning of the 20th century, researchers discovered that matter was not continuous and solid as it appeared. Instead, everything around us is made of atoms, incredibly small structures composed of a central nucleus surrounded by electrons. But what surprised scientists most was the structure of these atoms. Almost all of an atom is empty space. If the nucleus of an atom were the size of a marble, the electrons would be orbiting dozens of meters away. This means that the objects we perceive as solid are actually made mostly of emptiness. The reason we experience solidity is not because matter is truly dense, but because electromagnetic forces prevent atoms from passing through one another. As physicists looked deeper into the structure of atoms, they discovered something even more surprising. Electrons do not behave like tiny planets orbiting a nucleus. Instead, they behave like waves of probability. According to quantum mechanics, an electron does not exist in one precise location until it is observed or measured. Instead, it exists as a cloud of possibilities describing where it might be found. This idea challenges the very notion of physical reality. If particles do not have definite positions until they are measured, then the world may not exist in a fully determined state before observation occurs. This strange behavior becomes even more dramatic with a phenomenon known as quantum superposition. In quantum physics, a particle can exist in multiple states at the same time. For example, an electron can simultaneously occupy different positions or possess different energies until a measurement forces it into a single state. Experiments have repeatedly confirmed this behavior, demonstrating that the microscopic world does not follow the intuitive rules of classical physics. Another remarkable discovery is quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring one instantly affects the other. no matter how far apart they are. This connection appears to occur faster than light, seemingly violating the limits imposed by relativity. Einstein famously referred to this phenomenon as spooky action at a distance. Today, entanglement is one of the most actively studied aspects of quantum physics and plays a crucial role in emerging technologies such as quantum computing and quantum encryption. While quantum mechanics revealed the strange behavior of the microscopic world, Einstein's theory of relativity transformed our understanding of space and time. Before relativity, scientists believed that space and time were fixed and absolute. Time was thought to flow at the same rate everywhere in the universe, and space was seen as a static stage where events took place. Einstein showed that this picture was incomplete. In reality, space and time are woven together into a single structure called space-time, and this structure can bend and stretch under the influence of mass and energy. Massive objects such as stars and black holes distort space-time around them. Instead of gravity being a force pulling objects together, it is the result of objects moving through curved space-time. This means that space itself is dynamic and flexible. Even time can slow down in strong gravitational fields or when objects move at extremely high speeds. These effects have been experimentally confirmed and must even be considered when operating technologies such as GPS satellites. The more scientists explored the universe, the more they realized that the reality we experience is only a simplified layer of something much deeper. At the microscopic scale, particles behave probabilistically. At cosmic scales, space and time bend and stretch under the influence of gravity. And at the largest scales of the universe, astronomers discovered that most of reality is composed of mysterious components we cannot directly observe. Dark matter is one of these mysteries. When astronomers studied how galaxies rotate, they found that visible matter alone could not explain their motion. Stars on the outer edges of galaxies were moving much faster than expected. Something invisible appeared to be providing additional gravitational pull. Scientists concluded that galaxies must be surrounded by large amounts of unseen matter, now known as dark matter. Although dark matter cannot be detected directly, its gravitational effects are unmistakable. Even more mysterious is dark energy. Observations of distant galaxies have shown that the expansion of the universe is accelerating. Instead of slowing down over time due to gravity, galaxies are moving away from each other faster and faster. This acceleration suggests that space itself contains a form of energy pushing the universe apart. Scientists call this phenomenon dark energy. Together, dark matter and dark energy make up about 95% of the universe, meaning that everything we can see represents only a tiny fraction of reality. Black holes provide yet another example of how strange the universe can be. These objects form when massive stars collapse under their own gravity, compressing matter into extremely dense regions of space. The gravitational pull becomes so strong that nothing can escape, not even light. For many years, scientists believed that anything falling into a black hole would disappear forever. But quantum physics suggests something more complicated. Black holes may slowly emit radiation and eventually evaporate over incredibly long periods of time. This discovery created a profound puzzle in physics known as the black hole information paradox. According to quantum theory, information about physical systems cannot be destroyed. Yet, if a black hole evaporates completely, it seems that the information about everything that fell into it would vanish. Solving this paradox may require a deeper understanding of the relationship between gravity and quantum mechanics. Some physicists now suspect that space itself may not be fundamental. Instead, space may emerge from deeper relationships between quantum systems. In certain theoretical models, the geometry of space-time arises from patterns of quantum entanglement. If these ideas are correct, the universe may not be built from particles moving through space, but from networks of connections and information that give rise to the appearance of space itself. This possibility suggests that reality may be far more abstract than we once imagined. The universe could be fundamentally informational, with matter, energy, and even space emerging from deeper physical principles. Although these ideas remain speculative, they demonstrate how radically our understanding of the cosmos has evolved. Perhaps the most remarkable aspect of modern science is that the more we learn about the universe, the more mysterious it becomes. Each discovery answers some questions, but raises new ones. Instead of revealing a simple and predictable universe, physics has uncovered a reality that is complex, dynamic, and deeply interconnected. The universe is not merely a collection of objects floating in empty space. It is a vast system of relationships, interactions, and structures that we are only beginning to understand. And the deeper we look, the more we realize that reality may be far stranger than we ever imagined. Still, within